Welcome back, my friends, to the show that never ends. This is the last of the five chemical reactions we're going to learn about at the beginning of the year. Don't forget, there's 14 of them, but five is good. The fifth one is called combustion. Sometimes this is called burning in normal life, but combustion requires what's called a hydrocarbon. A hydrocarbon is a compound that's made up of hydrogen and carbon only. It combines rapidly with the oxygen in the air, and it only forms carbon dioxide and water. All combustion reactions give off a lot of energy. They're all exothermic. They all require energy to start, just like any reaction, but they give back a lot more energy. They give off a lot of heat. There's not much challenge in recognizing these because the only difference is what is the hydrocarbon. But whatever the hydrocarbon is, it combines with oxygen and it always makes carbon dioxide and water. It doesn't change. The numbers change because some hydrocarbons are little and some are bigger, and to balance it, you got to use different numbers. But it's a hydrocarbon and oxygen makes carbon dioxide and water. Every single combustion reaction looks exactly like this. Now, here are some examples of hydrocarbons that you've heard of. The first two there, methane and propane, they're both gases. They're little hydrocarbons. Methane only has one carbon. Propane has three. And when you have, probably three or less carbons in your hydrocarbon chain, the molecules are going to be gases at normal room temperature. But once they get a little bigger, butane only has four. But octane has 8 carbons in a chain. Those are liquids. Octane is gasoline. Put that in your car. Now, hydrocarbons can also be solid. Now, the word wax is a very loose word in chemistry. Wax is kind of for almost any hydrocarbon that's a solid. Now, hydrocarbons are sort of like chains of carbon surrounded by hydrogen, and we'll learn more about them another day. But once you get over 20 carbons in length, the molecules just get tangled up and they form solids. It's the same stuff, they're just really much bigger. And the hydrocarbons can get really long, 40, 50 carbons long even. So you could be a gas, a liquid, or a solid, but you can combine with oxygen really quickly and you form carbon dioxide and water as your products. The first example we're going to do here is methane. Methane is the simplest of all hydrocarbons because it only has one carbon. In fact, we'll see in organic chemistry the word meth, the prefix meth, M-E-T-H, means one carbon. Now, the skeleton for this is methane, CH4, it's a gas, combines with oxygen, which is a gas. It's going to make carbon dioxide, which is a gas, and water. Now, water is a weird thing. Even the word water means liquid, but because the combustion reactions are so hot, because they're so exothermic, usually the water is gas. Some of it might be liquid. We're not trying to fool anybody here with this little G. It's gas. If some of it happens to come out as an L, that's okay. We don't usually write water G plus water L. It's a gas. It's so hot. Some of it could be liquid. Don't worry about that. Hydrocarbon and oxygen makes carbon dioxide and water. This is the skeleton. All the formulas are written correctly. CH4 is methane. Oxygen is a Hunkelbrief twin. Carbon dioxide and water, those formulas you knew before you met me. So they're all right. Now, how do we balance a chemical reaction? We start at the beginning and we talk to ourselves. So, say this. There's one carbon in methane in the front, and there's one carbon in carbon dioxide in the product. Good, 1 and 1. There's 4 hydrogens in the methane, but there's only 2 hydrogens on the product side in water. How are we going to get 4 hydrogens over there? We have to put a 2 in front of the water, and then we have to start over. So here we have the 2 in front of the water. Now we're going to start over. Let's say it with me. 1 carbon in the front, 1 carbon in the back. Fine. 4 hydrogens in methane, 4 hydrogens in water. Good. There's just 2 oxygens in the reactant. We always start with just 2 oxygens in the reactant because we have O2. Now, on the product side, there are 2 oxygens in carbon dioxide plus 2 more oxygens in water. 2 plus 2 is 4. How are we going to get 4 oxygens on the reactant side in the front? Well, what do you think? We got to put a 2 there. Now we have to check. There's 1 carbon in the front, 1 carbon in the back. Good. 4 hydrogens in the front, 4 hydrogens in the back. Good. There's 4 oxygens now on the reactant side. And there's 2 oxygens in CO2 and 2 oxygens in water. That's 4, all balanced. Finally, we have to do what's called the John Dalton check. Do we have this balanced in the simplest whole number ratio? Did we get lost and get it bigger and bigger and bigger and get it to balance, but at a high, high level? Or is it at the most reduced level? We have 1 methane and 2 oxygens, 1 carbon dioxide, and 2 waters. This is in a 1:2 to 1:2 ratio. That cannot be reduced. That means we're good. And in purple there, it says, look, due to the heat released, the water is a gas. Methane gas, that's Bunsen burner gas. That's gas in my stove. It makes dang hot, very exothermic. The water is going to be a gas. The next one, we're going to do 2 in a row. They're both 89. We'll do 1 at a time. This stuff happens to be called propane. P-R-O, P-R-O-P, prop, means 3 carbons in this chain. So it's a bigger molecule, actually has a lot more energy. When this burns, it gives off more energy per mole than methane because there's going to be a lot more rebonding into carbon dioxide and water. And when bonds form, energy is released. So there's going to be more energy coming out of this. This is even more dangerous to use than methane. Well, we start out with the hydrocarbon. It combines with oxygen, and what's it going to form? It forms carbon dioxide and water. Right? Always forms carbon dioxide and water. Say it. There's 3 carbons in the reactant side, but there's only 1 carbon in carbon dioxide. So we have to put a 3 in front of the carbon dioxide, and now we have to start over. So there's 3 carbons in the reactant and 3 carbons in the product. Good. There are 8 hydrogens in propane. H8. There's only 2 hydrogens in water. So we have to put a 4 in front of the water so we get 8 hydrogens in the product. Say it again. 3 carbons in the reactant, 3 carbons in the product. Good. 8 hydrogens in the reactant, 8 hydrogens in the product. Good. We always start with 2 oxygens on the reactant side. Now on the product side, we have 3 carbon dioxides. That's 6 oxygens. And then we also have 4 more oxygens in the water. 6 and 4 is 10. There's 10 oxygens in the product. How are we going to get 10 oxygens on the reactant side? We have to put a 5 in front of the O2. And now we check. 3 carbons in the front, 3 carbons in the back. Good. 8 hydrogens in the front, 8 hydrogens in the back. Good. 10 oxygens on the reactant side. And we have 6 plus 4 oxygens in the product. It's balanced. What's John Dalton got to say about this? This reaction is in a 1:5:3:4 ratio. It cannot be reducted. That's supposed to say reduced. Oops, I made a little typo there. Can't be reduced. This is perfect. Except for reducted, whatever the heck that means. Here's the other one. C2H6. Now this only has 2 carbons. This actually is called ethane. All this stuff is real. It's not just letters and numbers we're moving around. This is a real compound. It's a hydrocarbon, combines with oxygen. What does it make? Well, if it's combustion, if it's a hydrocarbon and oxygen, it always makes the same thing, carbon dioxide and water. So how do we balance it? We start at the beginning. Glinda the Good Witch said, what do you do? Well, it's always best to start at the beginning. There's 2 carbons in ethane. There's only 1 carbon in carbon dioxide. So we put a 2 in front of the carbon dioxide and we start over again. So say it. 2 carbons in ethane, 2 carbons in carbon dioxide. Good. There are 6 hydrogens in ethane, but there's only 2 hydrogens in water. How are we going to get 6 hydrogens in water? We have to put a 3 in front of it, and then we have to start over again. So 2 carbons in ethane, 2 carbons in carbon dioxide. Good. 6 hydrogens in ethane, and now we have 6 total hydrogens in the water. That's good. We always start with 2 oxygens in the reactant side. Right? Now, in carbon dioxide, there's 4 oxygens, and then there's 3 more in water. 4 and 3 is 7. 7 is odd. Odd is not good. Now, we need to double the odd one, not all of the products, just the odd oxygen, and then we have to start over. This is kind of a pain in the neck now because we have to make the 3 H2Os, we have to double that to 6, which throws everything off, and then we have to keep going. So I have to change the 3 in the water to a 6 to double the odd one, and then I got to start over. So I have a 6 now in front of the water. There's 2 carbons in ethane, and there's 2 carbons in carbon dioxide, good. There's 6 hydrogens in ethane, but now we have 12 hydrogens in water. That's not good. How are we going to get 12 hydrogens in the reactant? We now have to put a 2 in front of the ethane, and we have to start all over again, and everything's a mess. So let's put the 2 in front of ethane, and we start all over. There's 4 carbons in ethane, but we only have 2 carbons in carbon dioxide because we put a 2 there before. We have 4 carbons in ethane. We need to have 4 carbons in the product. So I have to change the 2 in front of carbon dioxide into a 4, and I have to go back to the beginning again. So I changed that to a 4, and here we go. There's 4 carbons in ethane. There's 4 carbons in carbon dioxide. There's 12 hydrogens in ethane, right? 2 H6s. We have 12 hydrogens in water. We have 6 H2s. We always start with 2 oxygens on the reactant side. Now we have 8 oxygens in carbon dioxide and 6 more in water. 8 and 6 is 14. How do we get 14 on the reactant side? Look at the very bottom line. It says, how do you get 17 O's in the reactant? You don't. That would be dumb. That's a typo. Who the heck is typing these slides? How do we get 14 oxygens on the reactant side? We have to put a 7 there. Say it. 4 carbons in the front, 4 carbons in the back. 12 hydrogens in the front, 12 hydrogens in the back. We have 14 oxygens in the front. And there's 8 oxygens in carbon dioxide and 6 more. 8 and 6 is 14. It's balanced. What does John Dalton say about this? He says 2 to 7 to 4 to 6. John Dalton says, yay. We did it again. Every single equation will balance. Why won't it balance? Well, if you write one of the skeleton formulas wrong, it may not balance. It might. You still might be able to get the proportions to work, but it won't be correct. Or you just lose count. But most importantly, if it gets bigger and bigger and bigger, you might actually get something that's balanced, but not in the lowest or most reduced form. So you always do the John Dalton check at the end to make sure your ratio is really at the lowest level. Number 90, here's a new vocabulary word. A hydrocarbon is made of just hydrogen and carbon. There are things called oxygenated hydrocarbons. Now, oxygenated hydrocarbon means a hydrocarbon that's been stuck with some oxygen in it. And there's a lot of these, all right? Compounds that have carbon, hydrogen, and oxygen. There's a whole lot of them. There's ethers, and there's acids, and there's alcohols, esters. There's a whole lot of oxygenated hydrocarbons, and they burn really well. They balance a little more difficultly because now we have oxygen in both parts of the front and both parts of the products. So it's a little trickier because you got to pay more attention to the oxygens. The numbers sometimes get a little bigger. But so far, it's not so hard. We haven't even gotten a number bigger than 10. The numbers are small enough you can still use your hands. Here we go. Usually, I would combust some methanol for you. Methanol is an alcohol. You can't drink this kind at all right? Alcohol that's in wine and beer has 2 carbons. It's called ethanol. This is 1 carbon, methanol, outright poison. And it will burn when it's pure. Now, beer and wine and stuff like that, even vodka, that's not flammable because it's mostly water, right? But if it's at least 50% pure alcohol, then it could burn. But wine and beer and regular cocktail alcohol, it doesn't burn because it's actually less than 50% pure alcohol. It's a solution. But here we have methanol, which is a compound. Pure methanol can combine with oxygen and turn into carbon dioxide and water. Now, the methanol formula is kind of funky. Sometimes we write things unusually, and this is how we write this particular formula. It has what's called the OH group on the end. Now, we've seen OH before in an ionic compound like sodium hydroxide or barium with 2 hydroxides. That's an ionic polyatomic anion. Here, there's no ions. This is molecular. It just happens to be OH. And when you immediately see that it's not ionic because we don't have any metals, you realize it's OH group, which is different than a hydroxide. And OH groups indicate alcohol. So there's a lot of kinds of alcohols. This one is 1 carbon, and it's called methanol. Now, we're going to combine it with oxygen. It's going to form carbon dioxide and water, and we're going to try to balance it right now. So this is what the beginning part looks like. Methanol, CH3OH. That's how you would say that, CH3OH. It's a gas. Maybe it's a liquid. It depends on the temperature. Oxygen's a gas, and it's certainly going to form carbon dioxide gas and also water gas because it's going to be really, really hot. So how do we balance this? Let's start talking. There's 1 carbon in methanol, 1 carbon in carbon dioxide. Good. Now, the hydrogens, pay attention here. In methanol, we have 3 plus 1. We put them in different places in the formula, but they're still hydrogen. So we have four hydrogens. Now, there's a typo I'm going to fix right now because I can't take that one. This has to be an H. Sorry about that, kids. Let me save that, and we'll get right back to this. So there's 1 carbon in methanol and 1 in carbon dioxide. Good. There's 4 H's in methanol, but there's only 2 in water. So we have to put a 2 in front of the water, and we have to start over again. So there's the 2 in front of water. Start again. 1 carbon in methanol, 1 carbon in carbon dioxide. There's 4. Who typed this? There are going to be 4 hydrogens in methanol and 4 in water now. Good. There's 1 oxygen in the methanol plus 2 more in the oxygen. So there's 3 oxygens on the reactant side. But we have 2 oxygens plus 2 oxygens in the product. 3 in the reactant, 4 in the product. Odd and even. It's the odd one that's broken. Now, in the reactant side, we have 1 oxygen in methanol and 2 oxygens in oxygen. The odd one is the methanol. So we have to put a 2 in front of the methanol, and now we have to start over again. Now, once we put a 2 there, everything changes, and we're going to fight with this a little more. There's 2 carbons in methanol, but there's only 1 in front of the carbon dioxide. That's not good. So we have to put a 2 in front of the carbon dioxide, and we have to start over. So 2 carbons in methanol, 2 carbons in carbon dioxide. Good. Now in the front, we have 2 times 3 plus 1. There's 8 hydrogens in the methanol, but there's just 4 hydrogens in the water. So we have to change the water up to 4 waters so that we get 8 hydrogens. So now we got to change that number at the end to a 4. I did that in green. Look at this now. There's 4 waters, and we start over. 2 carbons in methanol, 2 carbons in carbon dioxide. Good. There's 8 hydrogens in methanol. There's 8 hydrogens now in water. Good. Now, there are 2 oxygens in the methanol and 2 more in the oxygen. That's a total of 4. Now, we have 4 oxygens plus 4 more oxygens on the product side, which is 8. There's 4 in the front and 8 in the back. How are we going to get 8 oxygens in the front? Let's not touch methanol, because as soon as we change the methanol number, everything else has got to change. So let's leave that alone. So if we need 8 oxygens on the reactant side, and we have 2 in the methanol, and we don't want to touch them, how are we going to get 6 more in the front? We have to put a 3 in front of the oxygen. Let's do a quick check. 2 carbons in the front, 2 carbons in the back. Good. There's a total of 8 hydrogens in methanol, and there's 8 hydrogens in water. Good. We have 2 oxygens plus 6 oxygens on the reactant side. 2 and 6 is 8. On the product side, we have 4 oxygens plus 4 more oxygens, 8. That's good. So it seems balanced. What's John Dalton say? Look at Uncle John. Uncle John's Band is a good song by the Grateful Dead. Uncle John's Band. That's what I was thinking when I typed that. This is in a 2:3 to 2:4 ratio that can't be reduced. Okay, we did it. Now this one's harder, right? There's oxygens everywhere. What a pain in the neck. Hurts right over here. You just got to do it. Butane. Butane is a regular hydrocarbon. It has 4 carbons here. Now, the butane in the little butane click-lighters that I use sometimes, you probably have at home too, the butane's a liquid, comes squirt into a little tiny hole so it turns to a gas. So I don't even remember if I wrote liquid or gas, but it's going to be okay either way. Well, I didn't write anything. Oh, I think I just didn't fit them, right? When you get too many letters, it's hard to fit, and I want to be able to write. But it's a gas, another gas, another gas, and another gas. 4 gases. Say it. 4 carbons in butane. There's just 1 carbon in carbon dioxide. We have to put a 4 in front of carbon dioxide, and we start over again. So there's that 4. See it? It's blue. Start again. 4 carbons in butane, 4 carbons in carbon dioxide. Good. There are 10 hydrogens. 10 hydrogens in butane. But there's just 2 hydrogens in the water. So we have to put a 5 in front of the water to get up to 10 hydrogens. And when we do that, now we got to start over. 4 carbons in butane, 4 carbons in carbon dioxide, good. There's 10 hydrogens in the butane. There's now 10 hydrogens in the water, good. There are 2 oxygens in the front, right? That's good. But on the product side, we have 8 oxygens. 8 oxygens in carbon dioxide plus 5. 8 and 5 is 13. 13, well, it's unlucky, and it's odd. Now, out of those 2, carbon dioxide and water, it is the water that has the odd number of oxygens. So we have to fix the water. We have to double it. So instead of 5 waters, we're going to change that to a 10. And that throws everything off, and we got to start all over again. 4 carbons in butane, 4 carbons in carbon dioxide, good. We have 10 hydrogens in butane, but now how many hydrogens are in the water? We have 10 H2s. That's 20. 20 is way more than 10. How are we going to make 20 hydrogens in butane? We're forced to put a 2 in front of the butane, and now we got to start all over again. So with the 2 in front of the butane, we have 8 carbons in butane, but we only have 4 carbons in carbon dioxide. That's not good. We need to double it. We need to change that 4 into an 8, and we're going to start all over again. Listen, you think this is a little pain in the neck? You should try typing these slides over and over and over. This is a lot. It's not that bad. When you do it on paper, you'll be okay. So we switched it to 8, and we start again. 8 carbons in butane, 8 carbons in carbon dioxide. Good. There's 20 hydrogens in the butane, and we also have 20 hydrogens in the water. Good. We always start with just 2 oxygens in the reactant side. How many oxygens do we have on the product side? We have 16 oxygens in carbon dioxide, and we have 10 more oxygens in water. That's a total of 26. How do we get 26 oxygens in the front if they come in pairs, the O2s? Well, we have to put a 13 then in front of the oxygen, that most unlucky number. And then we do a quick check. 8 carbons in the reactant, 8 carbons in the product, good. 20 hydrogens in the reactant, 20 hydrogens in the product, good. We have 26 O's, 26 oxygens on the reactant side, and we have 16 plus 10, that's 26 oxygens on the product. What does John Dalton have to say about this? A 2 to 13 to 8 to 10 can't be reduced ratio is perfect. We're really getting this. We're really getting this. Octane. Octane is gasoline. Gasoline has 8 carbons. We've been doing what? We had 1 carbon for methane, 3 carbons for propane, 2 carbons for ethane, 8 carbons. This is very, very energetic. Octane is very, very exothermic. Kids can fool around, right? You get one of those little click-lighters, butane with 4 carbons, you make a little fire, you could rub your finger through it, you could show how tough you are. It's really stupid to do. Gasoline with 8 carbons is terribly dangerous stuff. You should never, ever play with gasoline. People have gasoline. I have some in my garage. I put it in my lawnmower. My son puts it in the lawnmower. Finally, I don't have to do that. You can't play with gasoline. If you try to light a little gasoline on fire, you blow right up. Gasoline is very unforgiving. It is not a toy. It's not a joke. The amount of energy in octane is enormous compared to methane or butane or propane. This stuff is bad. You know where they burn this stuff? Inside giant steel car engines. It's crazy, crazy powerful. Do not play with it. It burns really well. And when we get to thermochemistry, we'll learn about how much energy actually comes out of a mole of this compared to a mole of something else. This is the bad stuff. This works really well, causes terrible explosions, makes cars that weigh thousands of pounds go really fast on a road, right? It'd be much harder to make your car run on methane. You could do it, but you wouldn't go as far, right? This stuff, very powerful. Here we go, octane. It's going to combine with oxygen. It's going to make carbon dioxide and water, okay? It says in top in blue, the phases were emitted for space, octane's a liquid, the other three are gases, right? When you have octane in your car engine, though, sometimes they spritz some of that liquid out, vaporize it, because there's more surface area, it's going to explode faster, you use less. Could be a gas, depends on how you're imagining it, but octane is a liquid. Say it, 8 carbons in octane, 1 in carbon dioxide. You have to put an 8 in front of carbon dioxide, and you have to start over again. 8 carbons in octane, 8 in carbon dioxide, good. There's 18 hydrogens in octane. There's only 2 hydrogens in water. So we have to put a 9 in front of the water, so we get up to 18 hydrogens, and then we have to start over. There's 8 carbons in octane, 8 in carbon dioxide, good. There's 18 hydrogens in octane, 18 hydrogens in water, good. Now we always start with just 2 oxygens in O2. But look at the oxygens on the product side. We have 16 oxygens in the carbon dioxide plus 9 more. 16 and 9 is 25. 25 oxygens in the product. That's an odd number. Now, which one of them is odd? Is the 16 odd? Is the 9 odd? So we have to double the 9 to an 18, and then we're going to have to start all over again. 9 waters won't fly. We're going to make it 18, and now we start over. There's 8 carbons in the reactant, 8 carbons in the product. So far, so good. 18 hydrogens in octane. How many hydrogens do we have now in the water? 18 H2s. That's 36. 36. How do we get 36 hydrogens in octane? Well, we got to double the octane now and put a 2 in front of it. Now give us 36 hydrogens, but we got to start all over again. Look what we did. Now we have 16 carbons on the reactant side, but there's only 8 in carbon dioxide. That's not good. How are we going to get 16 carbons on the product side? We got to change the 8 into a 16, and we got to start all over again. There's 16 carbons. We have 16 carbons in carbon dioxide. We have 36 hydrogens in octane. Now we have 36 hydrogens in the water. We always start with 2 oxygens in the front. How many oxygens in the product? We have 16 times 2, which is 32 oxygens in carbon dioxide. And we also have 18 more oxygens in water. 32 and 18 is 50 oxygens. That's the biggest number we've seen. 50 oxygens. How do we get 50 in the reactant side if they come up in pairs? We got to put a 25. Now there's a big number. You don't even have, look at these numbers, right? These are big numbers compared to what we've done. And if we do a quick check, 16 carbons front and back, good. 36 hydrogens front and back, good. 50 oxygens in the front. 32 and 18 is 50 oxygens in the back. What's John Dalton say? 2 to 25 to 16 to 18. These are big numbers, but listen, if you had $2, it wouldn't be so much. If you had $25, it's nice. Not that much. $16 or $18, these numbers are not that big. They're bigger than what we've seen, but they're not that big. This was hard, back and forth, keep changing, keeps changing, but it's not impossible. Okay, what's this say? The notes end here now, but this slideshow is going to keep going for review. I will probably make a Zoom for that too, all right? We're going to practice a lot more balanced equations, okay? Oh, it does say, look, there's at least one more important vocabulary word. Here, I'll give it to you right now, but you still have to do the work. When we have combustion, especially when we do reactions on paper,
and everything is what we call a complete reaction. There's no leftover parts. A hydrocarbon and oxygen makes carbon dioxide and water. But in real life, sometimes there's not enough oxygen for the reaction to go forward normally, but there's enough oxygen for something to happen. Unfortunately, if you have a furnace, like in my basement, I have a natural gas heat. Methane comes in by pipe and it burns with the oxygen in the air. It produces carbon dioxide and water, which goes out through my chimney. It doesn't smell, and it makes the house hot. Now, if by chance there was a problem in my furnace, this is why you got to get your furnace checked every once in a while, clean it out and stuff. But if by chance there's a limited amount of oxygen, now if you cut off the oxygen, the fire goes out and it's nothing bad, it's all good. But if there's less oxygen than normal, sometimes the products are not going to be carbon dioxide and water. They will be carbon, literally just carbon, solid, black, that soot, and it backs up in your chimney. And you also get water, carbon and water, and carbon monoxide, CO. Carbon monoxide is a poison, and if you breathe it, it can kill you. Not like a smell of it, and you can't smell it anyway, it doesn't smell. But the carbon monoxide, just like oxygen, can bond to your hemoglobin. Now, when you breathe, oxygen goes into your lungs, and the oxygen transfers into your red blood cells. And it bonds to the hemoglobin in your red blood cell. And as your red blood cells travel to your feet, say, in your feet, there's less oxygen in those cells than in the hemoglobin. And by diffusion, the oxygen comes out of the hemoglobin and goes into your feet, and your feet stay alive. And this happens all day long. Your body uses up oxygen, and it produces carbon dioxide. So the blood shows up, it lets more oxygen out and picks up the carbon dioxide and brings it back to the lungs. In the lungs, it gets rid of the carbon dioxide and picks up more oxygen, and this happens all day long. If you breathe carbon monoxide also bonds pretty tight to the hemoglobin, but there's no carbon monoxide in your body. So when this red blood cell that now has carbon monoxide and it gets to your feet, it has no oxygen to give. And so it just kind of gets pushed back to the lungs. But the carbon monoxide bonds stronger than oxygen, so it stays stuck. And so whenever you get carbon monoxide in your red blood cell, that particular red blood cell, it doesn't work anymore. Basically, it's dead. But it's not dead. It dies. It'll die. It might die not for a few weeks, but you're going to have to move it around. It's not going to help you. It's not going to be doing any oxygen transport. So the more carbon monoxide you breathe in, the more of your red blood cells basically become like zombies. They're like the living dead. They're not dead, but they don't work. And breathing carbon dioxide is bad. So there is something called incomplete combustion, which you need to see about. All right. See you in class. Bye-bye.